and welcome to this session where we are going to learn about adaptive RAG. Now, you might have seen a lot of videos on how to implement different kind of RAG frameworks, different kind of variations of it, starting from naive RAG up to different kinds of RAG, like RAG which uses graph DB, RAG which is corrective in nature, or different kinds of strategies in RAG, different kinds of tracking strategies and all of that. But today we are going to see how to implement a certain kind of RAG, a certain kind of workflow in RAG that helps us improve some of the limitations of naive RAG in an intuitive and strategic way. We're going to implement this adaptive RAG in a series of videos, and we are going to implement it on LangGraph. If you don't know about LangGraph, you can refer to my playlist on agentic workflows with LangGraph. So let's begin. First of all, you know how I break down my videos. First of all, directly jumping into the topic, we talk about the intuition behind it. Why should we even jump into that topic, right? So, first of all, the intuition behind this adaptive RAG. So adaptive RAG is basically trying to overcome some of the existing limitations of naive RAG. What is naive RAG? If you don't understand that, you can go through some of the videos. I'm preparing to create some introductory videos on RAG. If you require them, just put it down in the comment section. I'll work on them. But if you are straight up jumping into this video, naive RAG is basically a simple version of RAG where we are taking in a user query, chunking. We have already chunked our documents and placed in a vector store. We're taking in the user query, embedding it, doing a similarity match, getting the relevant documents from the vector store, and then plugging in the user query as well as the retrieved documents into a prompt, feeding that to an LLM and getting a response. So this is naive RAG, but it has got a lot of limitations. Some of the limitations which this adaptive RAG, which I'm going to talk about, is going to kind of, remedy. So let's go. First is diverse user queries. You know that in naive RAG, you kind of need the user to understand what kind of data do you have in your vector stores, right? For example, if your vector store is organized around information about, say, medical documents, then you expect the user to ask questions around medical documents, right? What if the user asks some other question? What if user asks something like, what is the scope of generative AI in medical science? Well, you don't have information about that in your vector store. What are you going to do in that case? Because based on your semantic search algorithm, it is still going to relevant some documents. And the answer that you're going to get is completely gibberish in that case, because you are not prepared for this question. Your vector store has limited information, but the user queries are diverse in nature. How are we going to work with that? In adaptive RAG, we use something called as a router, where we take in the user question, and if we find that the question is something which is unrelated to our indexed documents in the vector store, we route that question to our web search tool, and which basically searches the web and gets the answer from the web and provides the answer to the user. So this actually does a very big deal to ingest a diverse variety of user queries in your RAG application. If the user asks, what is the capital of Finland? If the user asks, how do medical robots work? There can be infinite kind of questions, and you need to have some kind of fallback strategy, right? So first is handling diverse user queries. Well, another aspect of this diverse user queries is, in RAG, we are basically expecting our user to provide us with an informed query, right? But not all users are actually good at writing prompts, right? What happens in that case is gibberish in, gibberish out, garbage in, garbage out. If the prompt is not well informed, it's not well structured in a way, it is kind of very loose, then the chunks it's going to retrieve are also going to be quite irrelevant, and we are not going to have a good response. So for that, in adaptive RAG, we have a rewriter node, which in case we are not getting relevant chunks from our vector store, it's going to rewrite the query through an LLM so that we can also provide good answers to not so good user queries. Second is irrelevant retrieval, bad answers. So it's very obvious that if the retrieval on the user query is getting irrelevant chunks which are not fit to answer that particular query, then we are going to expect bad answers from our RAG application. Now in a naive RAG application, there is literally nothing that we can do about it, because the user is going to see an answer which is not that good and he's going to believe that our RAG application is not working. So in this case, we need to have some kind of strategy where we understand or where we actually adapt for a case where the retrieval is just not good enough. So here you can see we have a step where if the documents are not relevant, we rewrite and then we do the retrieval again. I'm going to explain this in a minute. Third is hallucinations. Obviously, hallucinations is a big problem with LLMs. Sometimes you retrieve the right chunks, but the LLM chooses to provide a hallucinated answer, and we want to avoid that. So we have a step that checks for the hallucinations in this particular RAG framework. And fourth is fallback strategy. In any application that you develop, in any kind of work that you do, you need to have some kind of fallback strategies, right? Something where you think in a way where you are saying, what if this doesn't work? What if it doesn't happen properly? I need to have something to fall back to, right? So in this case, in adaptive RAG, we are trying to include some of the fallback strategies, and we are kind of assessing when to fall back and when not to fall back, when to go ahead with the user, when to go ahead with providing a response to the user query, and when to fall back to something else. So this is the intuition. Now we're going to jump into this particular adaptive RAG framework. So I'm going to explain this in a jiffy. User question, user asks a question. Before going for retrieval or web search, we have a router node. This router node is using an LLM and is kind of classifying the user query, if it should be sent towards the web search tool, or if it should be sent towards the vector store for retrieval and all this shit. So the router decides if the question is related to the indexed documents or not. If no, it goes to the web search tool to search the entire web, and it is very likely that you find an answer in the web for that. If you don't, we can have other routes as well, other paths as well in the future. So right now we are working with just 2 paths right now. The possibilities are limitless, as you can understand over here. So if the question is unrelated to index documents, it goes to web search tool, then goes to LLM node. The web search tool basically gets relevant information from the web, and we basically concatenate the user question with those chunks of information from the web, provide it to the LLM and get an answer. Cool, this is pretty easy. What if the question is related to index documents in vector store? Now, how do we decide if it's related or not? I'm going to talk about it in the notebook section where we are implementing this entire thing. If the question is related to indexed documents, then it goes to the retrieval step. The retrieve node basically retrieves the information from the vector store. Just a second. So here is the vector store, say. Okay, so this is the vector store. It's too big. Cool. It should be in central, right? Cool. The vector store, it gets information from the vector store. All right. So the retriever node, the work of the retriever node is to basically do a similarity search between the embedded version of user question and the indexed documents, indexed document embeddings rather in our vector store, and retrieve some relevant chunks, say 3 or 4 or 5 chunks, whatever we decide on. And then we go to the grader node. The work of this grader node is, the grader node uses LLM and provides an answer whether the documents are actually relevant to the user question or not. Are the documents fit to answer the user questions or not? So what it does is, for example, if we get 4 documents from the vector store, we retrieve 4 documents. For each document, it generates a binary score of yes or no, 1 or 0. So yes means that the document retrieved is relevant to the user question. No means that it is not relevant. So if docs relevant basically decides that, okay, if a particular document is relevant, then we go ahead. And if it's not, we rewrite the node. We rewrite the user query. Now here we can define a threshold. Say that if we have 4 retrieved documents, we can say something like, okay, if more than 3 or more than 2 documents are relevant, then you go ahead. If less than 2 documents retrieved are relevant, go for the rewriting part. Go for the rewriting. Don't generate any response from it. Okay, cool. So this is kind of fallback strategy where if we know that the retrieved documents are not relevant enough, we have a fallback strategy that we tell LLM. So this is also using LLM in background to rewrite the user query and again go for retrieval. And keep doing this until and unless we get a good set of relevant chunks that we can ground our answers in. So say that if the docs are relevant, more than say 3 docs are relevant or more than 2 docs are relevant, whatever the threshold we decide on, then we move forward and we go to the LLM node. LLM node is basically the one where we provide the user query and the retrieved chunks to generate a response. Now the response is generated over here. Second, we again check for hallucinations in that response. If hallucinations exist, then we want to again generate the response. If no, then go ahead. And towards the end, let's go to view mode. And then towards the end, after checking for hallucinations, we check if the answer is satisfactory. Now, what does this mean? We basically run a test using LLM. If the answer provided by the LLM actually answers the user question. If yes, go ahead and the answer is generated, voila. But if no, we again go for rewriting of the user query and we go for retrieval. Now this rewriting part is also called as query translation. If you want to read about it, query translation, if you want a detailed guide on it, I can tell you about it, just put it in the comments. But yeah, query translation is a big topic and is a growing topic. How do we rewrite the query in a better way? Cool. Now let's shift to the notebook. Good. Now in this notebook, I'm using a document for RAG. The document is basically a McKinsey report. Yeah, this one. It is titled as Time to Place Our Bets, AI Opportunity, blah, 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 blah. A lot of things in it, tables and stuff. So it's basically talking about the opportunities in AI or kind of the growth of AI in Europe markets. This is the document which I have indexed and stored in the vector store in this implementation. First of all, I've used this PyMu PDF for LLM. This is a new thing that has come up. You can check it. And I have ingested my document. Cool. After that, so here you can see my document. Just a second. MD text. Yeah, here you can see blah 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 blah, the entire document. Okay, cool. Now I have chunked this document using recursive character text splitter by LangChain, and the chunk size is 800, chunk overlap is 50. Now how did I reach this chunk size, chunk overlap? I just experimented with a few runs, reruns, iterative process, and I kind of got a feel for the document and I placed it. It's kind of arbitrary, but informed arbitrary. Okay. And then I created chunks, so you can see now what kind of chunks I have. Chunks 0, page content. So I have chunks in this way, and I have around, I think, 100 chunks or 200 chunks. Okay, I have 86 chunks. Ooh. Second, I've set up the vector store. I'm using Chroma for ease of use in the future. If I want to develop an application out of it, I might go for Pinecone or something which provides more functionalities and stuff. I might go for even Postgres or whatever you like. Currently, I'm using Chroma because it is very well integrated with the LangChain. Vector store and collection name is LangGraph. Retriever, I've set up a retriever runnable. So the retrieval runnable works. Let's check. So if I go for retriever dot invoke something like what is Europe's Gen AI strategy? Any question. Okay, I don't know if it even has the information to answer this. So we get 4 of these relevant chunks. Okay, a similarity matched chunks. I don't know if they're relevant or not. Okay, cool, it works. Now I'm setting up the router node, this particular node. So for router, we want the router to provide 2 kinds of responses. Okay? One is web search, second is vector store. So you know that if I want to get a structured output, or if I want to get a literal response like either vector store or web search, nothing else from an LLM, which is called as a structured output from an LLM, I can use this method with structured output and then provide a Pydantic class as an input. So I have created this schema for the router. And guys, if you don't understand any particular thing, because I know that I am talking of stuff right out of the air, but if you don't understand anything, you can put it in the comments and I'll try to create a video on that. And yeah. So I have created a schema called as router. And this router takes in an input path. So router user query to the most relevant path for response generation. Always remember that whenever you are using a Pydantic class which you want to feed to the with structured output method, always provide a good docstring. Okay. And then I want it to be literal, like either vector store or web search, nothing else. And then in field, I'm placing 3 dots because I want it to give a response. Oh, cool. And a description like given a user question, choose to route it to web search or vector store, blah blah blah. Okay. Setting up the LLM, chat OpenAI, GPT 3.5 Turbo and stuff. And the temperature has been set to 0 because I wanted to avoid any kind of creativity. I wanted to provide a structured response. Now one thing, a router has basically an easy task. It just has to provide a response like web search or vector store based on the user question and the preamble that I'm gonna give it. So instead of going for this GPT 3.5 Turbo, you can also go for some, some boutique models, some boutique LLMs like Cohere's Command R. I'm also going to create a video in the future maybe where I use that because it is obviously less expensive and there is not a lot of, utility drop in using that. Okay. And then this is the structured LLM router runnable that I have. And this is a preamble. So whenever we're using a router or any kind of structured output, we need to have a preamble, a proper preamble. So it is basically you are an expert at routing a user question to vector store web search. Now this is an important part, this particular prompt. The vector store contains documents related to Europe's competitive position, blah, 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 blah. So based on this particular description of my vector store, it's going to match the user question, whether it belongs to vector store or whether it belongs to web search. Now you might be thinking, how did I create this? Simply, I just uploaded my document to GPT-4 and I asked it to provide me an informed phrase. But yeah, if you have subject matter expertise, you may want to create this particular phrase by yourself as well. And then use the vector store for questions around these topics. Otherwise, use web search. Cool. Let me zoom in again. Root prompt is simply chat prompt template. It requires two things. One is system prompt, that is the preamble. Why is this called a preamble? Because this is the thing which the LLM is going to follow to provide response. It's also called as the preamble. And there is going to be a human question, that is a user query. Now we develop the router chain, taking the root prompt, after that the structured LLM router, and then we test it. So I'm testing it on this question. Root equals router chain.invoke. Question is, how much of Europe's productivity growth can generative AI potentially contribute, blah, 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 blah. Oh, it's a pretty complicated question. Let's see what the root tells us. It has provided a response that this question belongs to the vector store. So it's going to follow this particular path. But what if the question was very generic? Okay, let me create another. Router chain.invoke. Okay. Question this time is very generic. Let's take something like, what is capital of Finland? Okay. And then this time I want to print root 2. Let's see if it works. See, now it has given a response web search because this is a generic question and it is not related to Europe's Gen AI strategy or stuff like that, okay? So this is the job of a router. Assess the user query and set it off in the right track. Now, understand this particular flow of code. We're going to follow it for every single node, okay? What it's doing is, we define a schema whenever we want a structured output. We bind that schema to get a structured output out of LLM. We define a preamble or a system message, and then we create a chain. After that, we can invoke the chain whenever we want to get a response. So this is the kind of coding flow that we are going to follow. So this is the retrieval grader. So now we are working on this particular node called as the grader node. The work of grader node is to assess if a particular document is relevant to the user question or not. So again, we define a schema. In grade documents, the doc string is binary score for quantifying the relevance of the retrieved documents. And this time we want an answer yes or no. Nothing else. Again, I've used an LLM as ChatOpenAI. Again, I should set the temperature to 0. Not that it won't work without 0, but it's always good to have your LLM not hallucinating any manner when it's working with a structured output method. Again, I binded it. I provided a preamble to it. You might want to play around with the preambles and stuff like that to see how it works. These preambles I've kind of, just taken them from here and there, from different kinds of projects that I see along in the online world. So you're a grader assessing relevance of a retrieved document to user question. If the document contains keyword blah blah blah, grade it as relevant, give it a binary score yes or no. Now again, I feed it the chat prompt template. Now the chat prompt template has two inputs. First is a document. So this document is one of the documents retrieved by the retriever, and then the user question. So it matches these two semantically and sees if it's relevant. Then there is the grader chain, which is just a grading prompt, and then there are a grader. Then the question. This time I'm asking a question: which country in Europe has a leading position in AI semiconductor equipment manufacturing? And then retriever.get relevant documents. This is the retriever part, which I had set up while developing the vector store, while setting up the vector store. And then I'm taking the first chunk, first retrieved chunk from the retrieval, and I'm seeing that if it's relevant or not. So grader chain that invoke, and I have provided just the first because it takes one chunk per chain, Let's see what it says. Running, and it says no. Let's see what that chunk looked like. Doc text, let's print it. Okay. So according to it, this particular chunk does not play any relevance or any role in providing the answer to this question. Let's see if the second chunk is relevant. Again, no. Let's see what the second chunk look like. Let's see, second, third chunk. So this retrieval, it also gives you an kind of an understanding if your retriever is working properly or not. If you want to go with some other kind of chunk size, chunk overlaps, or retrieval strategies, like if you want to go for hybrid search, stuff like that, or if you want to go for different chunking strategies. So the grader can also help you assess the efficiency of a retriever. So now for the third chunk, it's saying that yes, it's relevant. Let's see how that looks like. And you see, this particular chunk is directly answering our question. Netherlands-based ASML is the market leader, and this is what the question was, which has a leading position. So it works pretty well, and it helps us understand which of the chunks are relevant and which aren't. Okay. So this was the grader part. The grader node is done. So you know how we work with LangGraph, right? We define each and every node, and then we set up the entire graph, and we put it all of them together, and then we define the flow. Cool. Now let's go to the next one, which is the response generation, which is the LLM node here. So it is pretty simple. Now I have pulled a particular prompt from the LangChain hub, which is a RAG prompt. It is nothing like very special. It's just a very simple prompt which says that based on the following context and following question, don't answer from anything outside the context, all those RAG stuff, Simple, very simple prompt. You can check out this prompt when you're working with this notebook. I will attach it in the description of the video. We set up the LLM, and then we set up a kind of a post processor for the retrieved documents, because we know that the retrieved documents are in this format. Where is it? Yeah, in this format. So we need to kind of, post process it to concatenate the page content part of all the retrieved chunks. This is what we are doing here. Join doc.page content for docking docs. And then we create a chain. Takes in the prompt, the LLM, and then the string output parser, which is just the kind of the last post processor to get the string part out of the LLM response. And then we check. So our question is going to be this particular question itself: which country in Europe has a leading position? And let's see how it works. We know that it's Netherlands, right? So okay, Netherlands has a leading position with companies like ASML with the market. Cool, it works. So this was the LLM node over here. Now we go to the other nodes. Now we are going to this particular part, hallucination checker. Our intuition behind this particular step or this particular node is we want to understand if the answer generated from the LLM node has got any kind of hallucinations or. So here we have defined another class where we want a binary score for indicating if hallucinations are present or not, and we want an answering yes or no. Cool. Again, we have an LLM. Again, I would like to set the temperature as 0. All right. And then we have a structured output. The preamble is pretty simple. You are a grader assessing whether a generated answer is grounded in or supported by a set of retrieved context. Give a binary score yes or no. Okay. Now, the hallucination prompt basically takes two inputs. One is the list of documents or all of the documents or all of the context which has been retrieved from the retriever, and the response which has been generated. It does not take the user question as an input because we want to understand if the response generated by the LLM is grounded in the retrieved chunks or not, or is it hallucinated, right? So this is kind of an assessment of the LLM's response. And then we create a chain following the same kind of format. Hallucination prompt, LLM hallucinations, invoke, documents, the entire list of documents from the retriever, and the response. Let's see. And the answer is yes. So basically, it is saying that this particular response has some kind of hallucination and is not completely grounded in the retrieved context. Okay. Now let's see what is the hallucination part. If you want to understand, now see, this is kind of troubleshooting. Okay. Now, if we want to understand what is the hallucination in this, there are multiple things that we can do. Copy this entire response and copy the entire context into the chat GPT, into Claude, Sonnet, anywhere, and just ask it to provide what is the hallucination. And then you can kind of, troubleshoot your RAG prompt or different kind of things. Now, the reason, if you ask me, why is it hallucinating over here? As I can see that it is not hallucinating a lot because it is providing the right answer. But the reason of hallucinating might be the RAG prompt, which we are pulling from the LangGraph hub, because it is a very, very simple prompt. Okay, we might want to have some kind of guardrails, kind of a more rigid prompt that prevents our LLM from hallucinating. Okay, cool. So if it's hallucinating, we again go for the response generation according to our graph, which we are going to develop later. Okay. Now, we are trying to develop the last part, this part, which is answer checker, that checks whether the answer is satisfactory or not. What it does is, it takes in the response and it takes in the user question, and it tries to answer the question if the LLM's final response is answering the user question or not. If it's not answering it, then we do not provide a response to the user yet. We go back to the retrieval after rewriting the question, so that something changes. We are trying to change something in every fallback. So we are grading the answer. We again want a binary response, yes or no. We can play around with this. Again, we have an LLM. Again, I would like to set the temperature as 0. And cool. And then structure output, grade answer. Again, we have preamble. You are a grader assessing whether an answer addresses or not. We are taking two inputs, the user question and the LLM generation, as I said. Creating the chain, invoking it. Let's see if it's answering our question or not. Okay, yes, it's answered clearly, because Netherlands is literally the semiconductor leader in Europe. So that's fine. So you see, although it's hallucinating, it is still answering our question. So that's the thing. Okay. So, okay, now we define this particular node, the rewriter node. That is our primary fallback strategy over here. We can think of multiple fallback strategies. The possibilities are limitless, as I say. But in this particular flow, we are falling back on the rewriter node. So I'm defining that node over here. It is an LLM that basically takes in the user question and tries to reframe it, modify the user question itself so that it is optimized for better retrieval. Because we know that the user might not be a very good prompt writer, but we need a good prompt to retrieve the relevant chunks, right? So you are a question, oh, I kind of stop, I don't know why I did that. You're a question rewriter that converts an input question to a better version that is optimized for retrieval, vector store retrieval, blah, blah, blah. So it basically just takes in the user query as an input and formulates an improved question. Let's see. So our question was, what was our question? Let's just see what was our question, okay? So that we can compare. Question. Our question was, which country in Europe has a leading position in AI semiconductor equipment manufacturing? The modified question is, which European countries are at the forefront of manufacturing AI semiconductor equipment? Cool. So this is the rewriter node. And then I'm trying to create the web search tool node, which is getting used in this path. It is very easy. We have seen how to create tools. So we can just import these tools from LangChain's community, and then we can define it this way, and you know how to use it. That invoke, say that if it asks any kind of question, which is, what is capital of Finland? Okay. And yeah. So you see it has basically retrieved, kind of retrieved or kind of searched and got these 5 answers from the web. We are using the Tavali search tool, and these answers we can feed to the LLM's context part, or we can directly feed to the LLM and get an answer for what is the capital of Finland. Cool. So in this video we have defined certain important nodes for this workflow. In the subsequent sessions we are going to create this entire flow and see it working. Cool. So thanks for learning. Let me know if you want to, because I've been throwing a lot of concepts from here and there, kind of Pydantic classes and chunking, splitting. I've done a lot of things in this. So this is not a beginner's session, obviously. So you might want to learn about some concepts that I've thrown around in this particular video. Just let me know in the comment section if you want to understand about any one of them further detail. So thanks for watching, thanks for learning, and stay tuned for more such videos. Thanks, bye-bye.